the green area. Okay, so we have this wavelength range. So, suppose this is the continuum of your, this is the spectrum of your object you are looking at, and suppose and I define the B band with this much. This much I call the B band, and this much I call the V band. Okay. This is B band. So if I take the difference between the magnitudes of these two bands, I get an idea of the color of the object I am looking at. If the object is red, so the continuum would be like this, and the V band magnitude would be much less than the V band magnitude. The object will be much lighter in the V band and much dimmer in the V band, right? And if the object is suppose in quite bluish, then this would be the spectrum, and the V band, its brightness in the V band will be much higher than the V band. So that basically gives me an idea of about the color of the object. And as I have mentioned, the absorption depends on the wavelength. So you need to take into account that. So that's why I am defining a quantity KB that is also dependent on the color of the object I am looking at. Okay, now I correct for the atmospheric absorption as Bi minus Kb times air mass. Okay, so this Bi naught is the magnitude of the object if there were no atmosphere between the object and my point of observation. Okay, so if Earth had not have an atmosphere, this would be Bi naught would have been its magnitude. And as you can see, this would be a smaller number than Bi, and that is, as I have mentioned, it is a negative logarithmic scale, so it is consistent with that. Now, you have corrected for the atmosphere, but depending on your place of observation, the kind of instruments you are using, the kind of the sensitivity of your sensor, this Bi naught may also vary. Right. So that's why look at the third expression. B is the standard value of the magnitude of the object you are looking at, and this has been this we know from observations over many centuries and all that. So this is kind of literature value, standard value of an object. Suppose Polaris. Polaris is a very good term. Suppose, for example, Vega. So Vega has a magnitude B. So that is a constant quantity. That is a standard value of Vega we have set, and we just compare these two values. So I am measuring this Vi naught, and this should be ideally the magnitude I should measure. I take the difference. Now this is a particular number, and this difference, as I have mentioned, will depend upon your place, from the place you are observing the object, and also your instruments you are using. Right. So that is in the right hand side you will see a term ZP. ZP is called the 0 point correction, and this actually takes into account there is a fixed value of this quantity for the particular instrument you are using, and the place of your observation or so that corrects for the observed value and the expected value. But there can still be some variations depending on some transient of the atmospheric effects, like there is a thunder somewhere or some light shown randomly. So there we put a slight tolerance level which is between plus minus 0.05, which also depends on the color of the object. So that is how we correct for the standard value and the observed value. Okay. Okay, now let's come to photometric system. So as you can see the definition, there is a list of standard magnitudes and colors measured at specific band classes for a set of stars that are well distributed What does that mean? So, okay. As I have mentioned, whenever you are making an photometric measurement, you are always taking data in a specific band. So this is your optical. This is in the visual range. This is some code we call G. This is in my visual range. This is R. You name it. There is a convention for that. I will come to it. But you divide the whole range where your sensor is sensitive into some specific bands. That is what is called band passes, and you take so that's okay. So look at the expression. There is a constant, and I am taking the difference between magnitude of two different objects. Now you can choose V2 and N2 in such a way V2 becomes 0 and N2 becomes for a particular value of N2, V2 becomes 0. So you will have a much simpler relation like Vi equal to minus 2.5 log N. This is the relation you can. This simplifies the equation. So for that you need to choose a particular object for which Bi becomes 0, right? So the choice of object depends on various factors as the band you are using and the region of the sky you are looking at. Okay, so for Johnson-Cousins systems we choose Vega as the reference star so that the Bi becomes 0, and for similarly for other systems. And note the word well distributed around the sky. Suppose you are standardizing your system with respect to a star in a particular region of the sky. So there is a very high chance that you are looking at some specific types of stars which might be of a particular which might be of similar ages, similar spectral types, and which might be at a similar distance from us. Because suppose you are looking at the band of the arm of Milky Way, so you are observing mainly the stars in our own galaxy. So the system you will get from there is not very general. So you need to choose stars that are well distributed around the sky, so that you can so that's how you make a standard photometric system. Yeah. Now let's talk about the UV VRI system. This is one of the most used and oldest standard photometric system. And this is also called Johnson-Cousins photometric system. And this system has been normalized with respect to Vega. So it has 5 bands, UV VRI, which starts from ultraviolet to visual, red and infrared. And if you measure the magnitude of Vega in any of the bands, the magnitude will always be 0. So that is what I mean by normalization with respect to Vega. And okay, so what are these curves? This is the response function of the system. So suppose this is the spectrum of your star. This is the spectrum of your star. This is the okay, you are measuring V band. Suppose this is your R lambda. This is F lambda. You multiply these two functions and take the integration, so you get area under the curve of the product of these two functions. That is how you and that is your magnitude in the specific band you are considering. So this is the integration. Okay. Similarly, there are a lot of bands, and it is not possible for me to go through all of them individually that are in use. Okay, this HDSS band is particularly very popular, and these are all broadband photometric systems. These are narrowband photometric systems, and they have their use in a lot of different scenarios. So you are basically considering the same wavelength range, and you are defining so many systems. Why? Because after measuring the magnitudes, you will do some science. You will model the stars and all that. For a particular type of stars, it becomes much convenient to the conversion equations becomes much simpler in particular systems. So that's why we find these different systems for your photometric measurements. Okay, if you want to learn more about the photometric systems, you can refer to this paper by Michael Fessel. It's a very good paper. Now let's go into the methods we use in photometry. So, absolute photometry. So as I've written this equation, for a system, suppose you are using Johnson-Hopkins system, you can always measure how many electrons my detector is collecting and use this formula to get the magnitude. But there is can you see a problem with this expression if you are taking data? Suppose when you are observing a particular object, a patch of cloud comes in front of the telescope. What will happen? The brightness will increase. Now the brightness you will measure, the magnitude you will get from that, it will not be the actual magnitude of the star, right? So how do you correct it? So for that, you take at least one other star from your target star in the same field of view. So suppose V is my target star. The brightness of this star, I want to study the brightness of this star. Now I have a different star whose magnitude I already know. I have measured its brightness and I have the standard value of this object. Now I'll use this formula and compare the amount of electrons or photons my sensor is detecting to get the brightness of my target star. That's how you can correct for the atmospheric effect. So suppose a cloud cover comes in front, so it will decrease the brightness of both the stars, right? So that's how you eliminate the errors. So this is called differential photometry, and that formula, if you use that formula, that is called absolute photometry for only one source. So this is differential photometry, and now aperture photometry. Another way you can eliminate the atmospheric effects, the clouds, light pollutions, is that suppose this is my object of interest, to put a circle around the object. Okay, this is what I call object aperture. Put another circle around that object, called inner circle or something. Put another circle around the object, outer circle, and there is no start, no other object in between these 2 points, the center and in this inside this outer circle. Okay, so I measure the flux inside the object aperture. Suppose it is a object, and measure the flux inside this smaller circle. I call it suppose F1, F5. Then I again measure the flux inside this bigger circle and call it F4. Now, if I subtract F4 minus F5, I will have the flux in this region. This is the region. What does this number mean? This corresponds to the brightness of the sky around the object, right? So you have the brightness of the sky just in the neighborhood of the object, and you have the brightness of the object itself in that particular condition. You can subtract the flux of the sky from the flux of the object apparatus to get the actual flux of the object of your interest. So even if a cloud cover comes in the field of view, it will just cancel out. The effect will just cancel out, right? So that is something called aperture photometry. And for measuring the fluxes in these apertures, you can use Python package called Astronomy. it has a lot of predefined, very useful, handy functions. So you can use that for determining the flux inside these circles. Okay. Okay. Now let's talk about the applications of photometry. How many of you have seen this diagram? This is called the Hertzsprung-Russell diagram. So you have luminosity and temperature as the axis. So depending on the type of the star, the age of the star, the stars occupy very specific regions in this luminosity time plane. So if I can if I know the luminosity and temperature of a star, I put it in this Hertzsprung-Russell diagram, and I know a lot of scalar parameters of that particular corresponding to that star, right? I know what are the elements in it, what is the age of the star, and how it has been created, things like that. So, now you want to know two things: luminosity and the temperature. So, as I have said, you have a lot of different bands. If you take the differences between the magnitudes of two different bands, you get an idea of the color, right? So these are called color indices. So these are some of the widely used color indices. And yeah, you know this relation, right? What is it called? So you assume the star to be a perfect sphere of radius r, and you assume that it is a perfect black body, and you know the luminosity. If somehow you know the luminosity, now what would be the value of temperature? If you know luminosity, the radius of the star, you can get the temperature of the star, temperature that fits the formula, and that is called the effective temperature of the object. So and this relation is for a very special typical star. It is not a general equation, okay? So it does not apply everywhere. So that is called effective temperature. Another application is that the interstellar radiation. Suppose you have eliminated the atmospheric effect, but there can still be interstellar dusts and gases in between you and the point of object of your interest. So that basically decreases the brightness of your object. So by studying with photometric analysis, you can know how much is the what kind of dust or gases is there in between in front of the object, or how much light is it absorbing. So that you can do, and it is called interstellar radiation. And the final thing I want to mention is the time series photometry. So you measure the brightness of an object of your choice, and you take reading over a long period of time. So you will see some distribution of the of your data points against time. So and depending on the shape of the curve you are getting, the shape of the distribution you are observing, you can know what kind of a variable star it is. So for a constant star, it would be just a straight line, straight horizontal line. But for a variable star, you will see a curvy plot, right? This kind of plots you will see observed for a eclipsing binary. When you have two stars orbiting each other and one star comes in front of the other, that basically blocks some light of the star behind it, and that is why you see dips in the plot. So this is for eclipsing binary. This kind of plots you will see for Cepheid variable. How many of you know about Cepheid variable? Have you heard about it? Okay, that is a very special class of Cepheid variables, and that has a great implication in determining cosmic distances. Okay. So, and this is the plot you will see for a RR line variable star. And this plot you will see for another type of variable star, which is Mira variable. I've worked on it in my internship period. So you can see some humps, periodic humps in the plot. Now, yeah. So once you have these plots, if the plot is periodic, you can get the period by some mathematical analysis, right? And that period can give you a lot of information, because there are astronomers have theoretically derived period luminosity relations, period age relations for particular types of stars. So if you know the period, you can get the luminosity of the star, and you can then again put it. Once you know the luminosity, you can place it in the Hertzsprung-Russell diagram, and you can get a lot of stellar parameters. You can get the age from the period to the age relation. The period luminosity relation is of particularly very important. This is the period luminosity relation for a classical symphony, and this is for type 2 symphony. This is for RI variable. You can see that this follows a linear trend. So if you know suppose you are observing a particular star, Pacific variable, and you get the period P, you can immediately know what is the luminosity, corresponding luminosity. Luminosity is what? The total amount of energy the star is radiating. So, and what you are observing is the apparent brightness of the star, and that apparent brightness will decrease as 1 by r square, as you know, right? As the further you go from the star, the dimmer it becomes. So the apparent brightness will be proportional to L by r square. From that, you can get the you can basically, if you know this quantity, you can get r. That is how you can measure the distance between you and the object of your interest. And she is Henrietta Leavitt, who actually observed this pattern between the period and luminosity for Cepheid variables. So just to give her the credit. Okay. And this concludes the talk. And in questions.
So will we take up questions for this after the second talk? So because we are running out of time.